All right, so today we're going to solve by square rooting. So we already know how to solve quadratic equations certain ways, right? So we know that when we have standard form, we can turn it to intercept form, and then we can use the zero product property to solve. But we also know that intercept and standard are not the only forms, right? There's also vertex form. So we need a way to solve when we're in vertex form. So in order to do that, we have a different method, and we use square rooting. But before we can talk about square rooting, we need to actually remember how to square root things and how to work with radicals. So we're going to start with our warm-up by working with radicals, okay? So you'll see in the warm-up, we're asked to just simplify different radicals. So what we're going to do is we're going to talk about one with a perfect square. Now, for each of these radicals, we don't want a decimal as our answer, right? So you'll see in the next one, it's not a perfect square. I still don't want a decimal, and here's why. I want the most precise answer possible, and if you are finding a decimal, like with your calculator, you are rounding, and that's not precise, right? So we want the most precise answer possible. Now, for this one, since it's a perfect square, we know that we can get a whole number out of it, right? A perfect square, we know that 7 times 7 is 49, right? We also know that -7 times -7 is 49, right? So there are two possible solutions to this situation, right? So our answer is plus or minus 7, right? We write plus or minus because that accounts for both possibilities, right? That's what when we write plus or minus, that's what we're saying. We're saying plus 7 or minus 7, right? Okay, so that's if we have a perfect square. You're just thinking about the number that multiplies to get that, right? Another way to think about this is square root of 49 equals the square root of 7 times the square root of 7, right? The square root of 7 squared. Well, squared gets rid of a square root, right? And that gives us the 7, and we also account for the plus or minus, right? So this piece is important. This idea that you can take a square root and you can pull it apart into square roots that multiply to give you that square root, because that's what we're going to do to simplify non-perfect squares. And I'll show you what I mean with the next problem. So here we have the square root of 27. You think about your perfect squares. You're like 1, 4, 16, 25, 30. I've already passed 27. It's not a perfect square. We can't actually square root this and get a whole number, but we can reduce it, and we're going to use the same strategy that we just used. We're going to say to ourselves, okay, well, square root of 27, that can be rewritten as the square root of 9 times the square root of 3, right? 9 times 3 is 27. Now, why did I do this? Why is this beneficial? Because we can do the square root of 9. Like, this part is something I can actually do, right? I know the square root of 9 is plus or minus 3, right? Always account for that plus or minus, because minus 3 times minus 3 is also 9. And then I have times square root of 3, okay? Well, when we have a number times a radical, it's kind of like with a variable. You don't actually have to write the times. So then I would say this is plus or minus 3 square root of 3, right? So that is another way we could do this. Or that is actually, I should say, the first way I've shown you how to do this. When you're reducing these radicals, you try to find a perfect square on the inside, right? We'll keep looking at examples so I can show you. This one, I kind of just jumped to the 9, but what if you didn't realize that 9 went into it? And we'll look at the next problem for that one. Okay, so let's say we have 3 times square root 120, right? So I'm sitting here and I'm like, I actually don't know what goes into 120 that might work like it did in the last problem. So what I do is I take 120 over to the side, and I think to myself, okay, let me just start from the bottom. I know the perfect squares are 1, 4, 9, 16, 25. Let me see if any of those go into it. I grab my calculator. I divide by 4, and I see if I get anything. Oh, I do, right? I get 30, right? So square root of 4 times square root of 30 will give me square root of 120. So I rewrite 3 times the square root of 4 times the square root of 30. Now I know I can reduce, or I can simplify the square root of 4. This becomes 3 times plus or minus 2 times the square root of 30. 3 times 2 is 6, so this is plus or minus 6 square root of 30. And then I'm curious, like maybe I can break down 30 more. Maybe there's more going on with the 30. So I try to break down the 30, right? And I think to myself, does 4 go into it? Does 16 go into it? Does 9 go into it? Does 25? Do any of these go into it? And it turns out no. Really, the only thing I could do here is say 6 and 5, 2 and 3. None of that is going to give me a perfect square. So that means this is fully simplified, and I'm done, right? This is more simplified than the original, okay? Let's keep going, okay? What if we had square root of 180? So same process, right? I'm not really sure what goes into it. I start dividing. So you could either start dividing by the lowest perfect square and keep going, or you can just think for a second and be like, well, 18, I know 9 goes into 18. Well, so 9 probably goes into 180, right? And you could rewrite this as square root of 9 times the square root of 20, right? But remember how at the end there we kind of looked at 30? You can do that right at the beginning. You can keep trying to break this down. So I asked myself, okay, does a perfect square go into 20? Well, yeah, 4 goes into 20, right? That's 4 and 5. So this becomes the square root of 9 times the square root of 4 times the square root of 5. Okay, we have a few things we can do here, right? Square root of 9 is plus or minus 3. Square root of 4 is plus or minus 2, and then I had the square root of 5, right? So I know that this is 2 times 3 is 6, so plus or minus 6 square root of 5. And I know that I can't break down 5 any further. Nothing goes into 5, right? Other than 5 and 1. Okay, so a couple more, and we'll get to the lesson. So here we have 324. Big number. Now, maybe you are really good at your perfect squares, and you know this is actually a perfect square. And you just know that this is plus or minus 18, right? Then you're done. But this is why the method works, right? Because even if you don't know that perfect square, maybe you don't only know them up to 10, that's fine. Because the other method still works. I can say, okay, 324, let me try to break that down a little bit, right? So I divide, I take a calculator, I divide. So I grab my calculator, I say, well, 324 divided by 4. Oh, interesting. 4 and 81. And then you notice, wait a minute, those are both perfect squares that I do know. I know that that's a perfect square, and I know that that's a perfect square. So I can say, okay, square root of 4 times the square root of 81, right? And this gives me plus or minus 2 times plus or minus 9. Well, what is 2 times 9? 18. So I get plus or minus 18 anyway, right? And let's say you divided 324 by 9. You would still get, 16, or 36, I should say. So 3 times 6 would give you 18 as well. So this would work even no matter how you decided to break it down, and you would get to this plus or minus 18, that same answer as everybody else. All right, one more example. Here we have the square root of 42. So you ask yourself, okay, I'm not sure if I can break this down at all. So you start to take it over here. And you think, well, I know my perfect square is 1, 4, 9, 16. Like I start dividing, right? Start dividing everything. And then I realize, okay, I don't think any of this works. So I know 6 and 7 go into this. And then I can do 2 and 3. There's no perfect square in there, right? If that's the case, this might happen. Just circle your answer, you're fully simplified, right? So that might happen. You might get an answer that you thought you could break down, but it's actually fully simplified. All right. So that method that I've shown you is one of your two options for breaking down. So we're going to talk about two options for breaking down radicals. One is where you know some perfect squares that you can work with. And the other one is I don't know perfect squares at all. And that's okay. We'll talk about that. Your first option is you're going to do what we just did. Find perfect squares inside, right? Inside the number you already have, right? So you have 108, and you just start asking yourself, I don't know, maybe perfect square goes into this. So I divide by 4, right? And if I divide by 4, I get 27, okay? And then you kind of want to keep looking, see if there's more perfect squares. And then so you realize 9 goes into 27. So divide this by 9, and you get 3. So you can, because you broke it down like this, 4, 9, and 3, you know that 4 times 9 times 3 gives you 108, right? That's just how our number trees work, right? So this is actually the square root of 4 times the square root of 9 times the square root of 3, right? So then this becomes plus or minus 2 times plus or minus 3 times the square root of 3. 2 times 3 is 6, plus or minus 6 square root of 3. And that is fully simplified because I can't break 3 down any further, right? Okay, so that's one method. That's if you know your perfect squares. But if you don't know your perfect squares, the only thing you need for this method is to be able to count to 2. All right, this is what's called the jailbreak method. And it's called the jailbreak method because we're going to think of the square root as like a jail, and the numbers are trying to break out, right? And there are certain rules for breaking out, right? So in order to do this thing, we need to break down our number all the way. And I'll show you what that means, right? And by the way, both methods get you the same answer, right? So let's say I have 108, and I want to break it down all the way. I'm not looking for perfect squares right now. I'm just breaking it down. So I start small, 2, 3, something like that, right? Does 2 go in? Yeah, 2 goes into this, right? 2 times 54. Then I keep going. 2 and 27, right? And then I notice 2 doesn't go into this, but 3 does. So 3 and 9. And then 9 becomes 3 and 3. So I created this big factor tree, right? And I've broken down 108 as much as I can break it down. I know, because of how factor trees work, that 2 times 2 times 3 times 3 times 3 is 108. So I've broken it down all the way, and those are the factors, right? So what I do is I rewrite this all as one big radical, and I write the numbers like they are multiplied. So that means I'm going to write 2 times 2 times 3 times 3 times 3. Okay? So I've broken it down all the way. Now, the rule here is to break out of this jail, you need a partner. And only one of you is going to make it, right? So I look for pairs. Now, that's the trick, but why do we do this? Remember, square root of 49, well, that's square root of 7 times 7, right? And what did that end up being? It ended up being plus or minus 7, right? Well, one of the 7s got out, and then one of them went away, right? So you had 7 on the outside, nothing left on the inside, plus or minus 7. It's a pair that was within the 49. So we're looking for pairs inside here. I get this pair, and then this one's on its own, right? So this is how it works. Within each pair, one escapes to the outside, and one doesn't make it. So it goes away. One escapes to the outside, and one doesn't make it, right? And then whatever doesn't have a pair just stays. So on the outside, I end up with, I have 2 times 3 on the outside, and on the inside, and I should say plus or minus, because we're always plus or minus when we square root. On the inside, all I have left is 3. 2 times 3 is 6. plus or minus 6 square root of 3 is my answer. It's the same answer I got when I knew my perfect squares. So you have a couple of options for breaking down these radicals, okay? Now, that's just a little review on breaking down radicals, right? And simplifying them. We need that skill for when we solve using square roots. So let's talk about solve using square roots. So when you're solving using square roots, there's two scenarios where you might solve using square roots. The first we've done already. When you're missing your bx term, one of your options is to solve using square roots. So for instance, if you have y equals x squared minus 16, right? You don't have your bx term, ax squared plus bx plus c. There's no bx, right? So we can solve using square roots. We would set that equal to 0 and then solve from there, okay? The other situation where you would solve using square roots is if you have vertex form. Which of course is y equals a times x minus h squared plus k, right? Those are your two times where you could solve using square roots, and you want to be able to recognize when you have those situations. For both of these, our steps are as follows. First, I'm going to isolate, meaning get by itself, the square. So whatever is being squared gets isolated. So for instance, in this situation, what was being isolated? Well, x squared is the square. So that means I have to get that by itself. I have to move everything away from it. That's what's being squared. So that's what I isolate. Now, in this situation, I would isolate the square. Well, what's being squared? This is being squared. X minus h is being squared, right? That's what's being squared. So that's what I'm going to get by itself. So that means I need to move the k, move the a, right? And we'll talk about how to do that. Okay, so once you've done those, right, you've isolated the square, now you're ready to square root both sides. Okay, you square root both sides. Make sure you plus or minus, because when you square root, you plus or minus. And then finally, the last thing I'll say is you might need to clean up a little bit, combine some like terms. It's going to depend on the situation. So I'll talk about that when we go through examples. All right, so what we're going to do is we're going to look at 3 examples where you're missing your bx term, and then 3 examples of vertex form, and then we'll be done. Okay, so remember, isolate the square, square root both sides, clean up. All right, so here we go. Usually it's y equals, and you have to turn it into 0. Here it's already set to 0 for you, so that works out fine for us. All right, so the first thing I want to do is isolate the square. Well, it means I need to get x squared by itself, right? Well, how do I get x squared by itself? I got to move away anything else that's there. So minus 49, I'm going to plus 49 on both sides. And that gives me 49 equals x squared. Our second step was to square root both sides. So I would square root over here, square root over here. On this side, I get x. On this side of the square root of 49, we already talked about how that is plus or minus 7. Now, remember what this means. You're finding solutions. You're saying these are your solutions, meaning these are the things that if I plug them in, it would make this true. So plus or minus 7 is fine to write. But you got to make sure that you understand what this is saying is x equals 7 and x equals negative 7. There are 2 solutions here, right? Both of those would make the equation true. All right? That's example 1. All right, example 2. Isolate the square. This is my square, right? So I'm moving the 12 over. Plus 12, plus 12. I get 12 equals x squared. Second step is the square root. Square root, square root. I get x equals square root of 12. Now, if I have the square root of anything that's not a perfect square, I have to do what we did on the front where we check for whether or not I can break it down. So I take 12 over here, and I say, well, let's see. Are there any perfect squares that go into 12? 4, right? 4 goes into 12 3 times. 4 times 3, right? So this becomes square root of 4 times square root of 3 equals x, or plus or minus 2 square root of 3 equals x, right? So those are your solutions. Those are the things, those are the two things. And when I say 2, I mean x equals 2 square root of 3 and x equals negative 2 square root of 3. Those are the two things that if you plug them in here, it would make this true. It would be this 2 square root of 3 squared would become 12. 12 minus 12 is 0. Okay? Always think about your solutions in that way. All right, one more example of that type. Again, we're going to isolate the square. So I add 21 to both sides. I get 21 equals x squared. Square root both sides. And I get x equals, and then I have square root of 21. Now, I'm going to write plus or minus the square root of 21. Even though 21 cannot be broken down, right? 21, that's 7 and 3. There's no perfect square in there. Even though I can't break it down, I write plus or minus because both plus square root of 21 and minus square root of 21 would make this true, right? Minus square root of 21 times minus square root of 21 would become 21 minus 21, which would make this true. It's also because thinking about our x-intercepts, we would have two x-intercepts for this equation, right? So we would need both solutions, right? This tells me the answer is x equals square root of 21 and x equals negative square root of 21, okay? All right, so those are 3 examples where we are missing the bx term. But now we got to talk about vertex form, okay? So we will talk about vertex form next, right? Same thing. I'm going to isolate the square. The square here is this, right? That's what's being squared. That's what needs to be isolated, that whole thing, meaning this has to go away. So I'm going to add 16. I'm going to add 16 to both sides, and I get 16 equals x minus 3 squared. So we've isolated the square. It's by itself. Now the next step is to square root both sides. So I square root here, and I square root here. What happens? Well, on this side, square root of 16 is plus or minus 4. And on this side, x minus 3 squared, square rooted, becomes just x minus 3. Okay, again, this is where the plus or minus understanding really matters. Because right now, what we're going to do is we're going to say, okay, there are 2 things being said right now, right? Plus 4 equals x minus 3 and minus 4 equals x minus 3. So at this point, we're going to pull this apart and say, okay, 4 equals x minus 3 and minus 4 equals x minus 3. Both those things are being said there, so both those things are true. And then I solve each one for x. So add 3, and I get x equals 7. That is one solution, right? And then over here, I would add 3, and I would get negative 1 equals x as my other solution, and both of those would make the original equation true. If I plugged in 7 here, think about it. 7 minus 3 is 4. 4 squared. 16 minus 16 is 0. Negative 1 minus 4, that would be negative 4 squared. Negative 4 squared is 16. 16 minus 16 is 0, right? Okay. So we always want to account for both solutions. All right, let's look at another example. Again, isolating the square, which is right here. So plus 36 I get 36 equals x minus 4 squared. square root, and I get plus or minus 6 equals x minus 4. Now I'm going to pull it apart into two equations, one that says 6 equals x minus 4, and one that says minus 6 equals x minus 4. And then I solve each one, add 4, 10 equals x. Here I would add 4, negative 2 equals x. And those are the two solutions that would make this equation true. That would make that true. Okay? Okay, so those are two pretty clean ones. Let's go over one more example that's not as clean and show you how to deal with that. Okay? Here we have 0 this is vertex form, right? 0 equals x plus 2 squared minus 45. My square is right here. That's what I need to isolate. So I'm going to move the 45. I'm going to add 45 to both sides. That gives me 45 equals x plus 2 squared. Now I square root both sides. And I get plus or minus the square root of 45 equals x plus 2. All right, so think about what this means. Two different things at the same time. One is I got plus or minus, so I got two different situations. The other thing is 45 might be able to be broken down. So I think, okay, 45, and then I realize 9 goes into that. That's 9 and 5. So really, this is square root of 45 equals square root of 9 times the square root of 5, or plus or minus 3 square root of 5. So that goes into this spot right here. So now I have plus or minus 3 square root of 5 equals x plus 2. Okay, so the last thing I want to do here is pull this apart. And I say, okay, that means two things. That means 3 square root of 5 equals x plus 2, and minus 3 square root of 5 equals x plus 2. Both situations, I'm going to solve for x. So I minus 2, minus 2, minus 2, minus 2. Now what happens here? I have negative 2 and 3 square root of 5. Those are not like terms. I can't bring those together. Whenever we don't have like terms, we just write them side by side. Number first, radical second. So I would say negative 2 plus 3 square root of 5 equals x. And that's my solution as it's written. I can't combine it any further. Here, I would have negative 2 minus 3 square root of 5 equals x. And that's my other solution. And believe it or not, those are the two things that if you plug them into that equation would make it 0. It's not as easy to see that as it was to check our other work, right? Which is all the more reason why we need these strategies to help us find our answers, because there's no way I would have come up with negative 2 minus 3 square root of 5 by looking at that and trying to guess and check, right? So that's why we use these strategies, these procedures to help us, okay? So again, isolate the square root both sides, and then clean it up in whichever way you need to. Sometimes there's a plus or minus you got to pull apart. Sometimes you got to move something over to solve for x, right? So each time there's a little bit of cleaning up to do. All right, so that is the lesson. Thanks. So the difference of perfect squares. So perfect square and difference, those are our key words. Let's talk about each word. What is a difference in math? What does it mean for there to be a difference in math?
Something's been subtracted.
Say it again? Subtraction, and that is key. There's a reason I'm making a point of pointing out this word, because it's not the addition of perfect squares. If it's adding, you can't do what we're about to do. It's just subtraction, okay? So make sure you're looking for that subtraction. Now let's talk about the word perfect squares. What's a perfect square? I know there's not a lot of you today, but help me out. Yeah, it's a number that when you square root you get a whole number, right? You get a nice number. So for instance, give me an example of a perfect square.
64.
64. What else?
9.
9. Any others? 16, right? Over there in those red boxes. The most common ones are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. And they keep going. You can keep going with perfect squares, right? So that's what we know a perfect square to be. And we're talking about the difference of perfect squares. So what are we talking about? So you might get a situation like this. X squared minus 9. Okay? And I said it was the difference of perfect squares. So do we see the difference part? Subtraction, right? Subtraction is the difference. Right? Do we see a perfect square? 9. Right? But wait a minute. I said the difference of perfect squares, plural. So where's the other perfect square?
1.
Not 1.
2.
What else can be square rooted here?
X.
X squared, right? So we need to add to our definition of perfect squares. Also, any variable you can square root and get another variable. Okay, so x squared is an example. Y squared, z squared. But what about more exponents? Any higher exponents we could square root and get something?
Power 4.
Yeah, you could square root x to the 4th, right? X to the 4th square rooted would be x squared, because x squared times x squared is x to the 4th. X to the 6th, right, would be x to the 3rd times x to the 3rd, right? So those are perfect squares, even though you might not think of them.
So in case 9.
It would be 6 because
It's addition.
you add the exponents, yeah.
So in the case of variables, for it to be a perfect square, the exponent has to be even.
Exactly. Yeah. You can square root an even exponent. Yeah. All right, so why do we want to know this? Why do we care about this? Because if you have x squared minus 9, say you have x squared minus 9, and you're told to solve it. We learned one way. We learned you can move the 9 over, you could square root both sides. Both ways work. But you could also say, oh, wait a minute. I know that that is x minus 3 times x plus 3. Right away, I know it's because a perfect square, that'll happen every time. If you think about it, if we do the magic x, I would have the bx term would be 0. The c is minus 9. The only way to add to get 0 is if you had the same number plus and minus, right? So it's always going to be that square root of the number, plus and minus, did. So you get this, and then you could solve from there, and you would get x equals 3, x equals negative 3, which is the same number you would have got if you moved 9 and square rooted both sides. You got plus or minus 3. Question?
Can we say x equals plus or minus 3?
Yep, you could say x equals plus or minus 3. So we're going to define this whole thing, but this is basically the pieces and example. Now we'll give the formal definition, okay? So the formal definition, or the formal way that you can write this, you would say x squared, I don't like that, x squared minus b squared, right? So you have two perfect squares. That b would usually be a number. Is always going to be x and b, so the square root of both minus plus every time, okay? That is a shortcut that can save you a lot of time if you can see it, right? So that's why I want to make sure to include it, okay? So x minus b, x plus b. So for example, x squared minus 25, we know right away is x minus 5, x plus 5. Okay? Now, that also means that our solution will be x equals plus or minus b, right? Those will be our x-intercepts, those will be our solutions. Okay? So we're just going to practice with like 4 of these, and then we'll move to homework review, okay? All right, so let's take a look at some examples. If you got x squared minus 100, first thing you would do, you'd set it equal to 0. Now, in the last class, we talked about how to, when you're missing your bx term, you would move it over, you would square root both sides, you would find your answer. You can do that. It would give you the same answer, but this is a shortcut. You know the square root of x squared is x. The square root of 100 is 10. So you have two perfect squares. So that means you could rewrite this as x10 minus plus, and now you can solve from there. X equals 10, x equals negative 10, or in other words, x equals plus or minus 10. See how quick you can do that when you know you have a difference of perfect squares. Okay? All right, so let's try another one. X squared plus 25, set it equal to 0. And then what would it become?
5. x5 plus minus.
Anybody have a different answer? Look closer. What's the name of this property, this trick that we're doing?
Zero property.
No, the thing we learned today.
Difference of perfect squares.
The difference of perfect squares. Is this a difference?
No.
This is not a difference, and this is the biggest mistake people make, and that's why I included it. I'm not trying to trick you. People get so into this because it's so quick that they see this and they get right. They go, "Oh, two perfect squares," but there's no difference, so you have to solve this another way. This is not subtraction, so you can't do your difference of perfect squares. Can't do it. You would have to do it another way. 25 on both sides, square root, minus 25 on both sides. Okay? Ready for the next one? All right, next one. 2x squared minus 32. We would set this equal to 0. And we would be like, okay, I don't see any perfect, 32 is not a perfect square. 2x squared is not a perfect square. Yes, but they're both divisible by 2, so maybe we GCF this. And I go 0 equals 2, and then I divide them both by 2. I get x squared minus 16. What do we notice? Perfect square, difference. We can do our thing, right? So this is 0 equals 2, x minus 4, x plus 4, and x equals 4, x equals negative 4. You're done. Pretty handy, right? All right, one more. X squared minus 20. So 0 equals x squared minus 20. What do we notice?
It's a difference, but it's not a perfect.
It's a difference, but it's not a perfect square, right? Not perfect square. So how would you solve this? Because you couldn't do the difference of perfect squares. Yep, you would have to solve this by square rooting, right? Is that what you're going to say? Yeah. So plus 20 plus 20, and you get 20 equals x squared and then you would square root. You'd get x equals plus or minus the square root of 20. And then what else would you want to check for? Are we done? We know we're done?
See if there are any perfect squares inside of it.
Yeah, you want to see if you can simplify that. So I would say, okay, let's see if there are any perfect squares inside of 20, like numbers, multiples, factors, I should say. Yeah, 4 is in there. So 4 times 5, I can change this. I can say this is plus or minus the square root of 4 times the square root of 5 equals x. And square root of 4 is 2, so this becomes x equals plus or minus 2 square root of 5. And I can't break 5 down any further, so I'm done. Okay? Got to be able to recognize the difference, know what to do in each situation. Make sense? Okay. And that's the end of the lesson. So 10. Okay. So you set it, first you set it equal to 0. You say 0 equals 3 times 2x plus 7 squared minus 27. So it's a weird vertex form, but it is vertex form. We don't usually see a number in there. You don't need to worry about that part. Now, if you had 0 equals 3y minus 27, what would you do to get y by itself? Well, not first. What would you do first? You can't divide before you... Well, you got to get rid of the negative 27, which we would add. Add 27 to both sides, and then we would divide by 3, right? Because we're trying to isolate the y. We're trying to get that y by itself. What you need to think about this term, you need to isolate the square. Sometimes it'll be x squared, and you isolate that. Sometimes it's a big thing being squared. So you're trying to get this by itself, so you can square root it, right? So you got to get rid of everything around it, which is negative 27 and 3, and you do it in the same order you would do this, okay? So what are we going to do first? Add 27. And I get 27 equals 3 times 2x plus 7 squared. Now, I can't do anything with this because it's being squared, so I still need to get rid of the 3, right? I can't square root this until I get rid of that 3. So I would, what's the 3 doing to this? Multiplying, so I divide. Divide by 3, divide by 3. Go over here. I get 9 equals 2x plus 7 squared. Now what can I do? I have my squared thing on its own, so I can square root it. Yep. Square root. I get plus or minus 3 equals 2x plus 7. So that means I have two situations. I have 3 equals 2x plus 7, and I have negative 3 equals 2x plus 7, and I just solve each of those. Okay? So that would be minus 7, minus 4 equals 2x, divide by 2, x equals negative 2. Here, minus 7, negative 10 equals 2x. Divide by 2, x equals negative 5. Does that make sense? So treat this as if you had like x squared, right? What would you do if you had x squared? You'd move everything away so you could square root it. Same thing. You got to square root that big thing. Okay? Does that make sense?
Yep.
All right. Other questions? Front or back? 11. Where's that in the back? Okay. So in this section, you had a bunch of situations, right? You had this, you had this, you had this, you had this. And you had to think about what we've done in the last few lessons. Is this a situation where I need to factor it, use the zero product property, or is this a situation where I need to isolate the square root both sides? So if we're looking at this situation, right, Which situation is it? The first one. Like I would say, okay, 0 equals x squared minus x minus 72. What can I do to solve this since it's in standard form? Yeah, I would factor it and move it to intercept form, right? And that would give me zero product property, which would allow me to solve it, right? So I would say, okay, I got minus 72 on top, minus 1 on the bottom. That's minus 9 and 8, right? So that becomes 0 equals x minus 9, x plus 8. And that means x equals 9 and x equals negative 8. And I have solved it, okay? So you got to recognize the situation, which one it is, and then go from there. Yeah?
On 14, it says to use square root.
Mm-hmm.
When I looked at like the answer key, wouldn't it be easier because you can do both in that situation? Wouldn't?
Yeah, anytime you're missing your bx term, you can technically say 0 is your bx, and then you can do magic x. The problem here is you don't have a GCF.
Oh.
Because 81 doesn't divide by 4. So square root would get you a easier answer because you wouldn't have to do decimals in your magic x, which we've never done.
Yeah.
So do you want to see it with the square root?
No, I figured that.
Okay. Does anybody else want to see 14? No? Yes? No? Any other problems we want to see? So we're good? Okay. Just to let you know in this one, because there's something I haven't taught you yet. You end up doing the square root of 81 over 4, like the fraction. And when you have that situation, you can say, oh, that's the square root of 81 over the square root of 4. You can pull it apart, and that gives you plus or minus 9 over 2, and that's how you would do that.
That's a lot easier.
Yeah, once you know that, it's pretty quick. I just want to make sure we knew that. Okay? All right.